Okay, I was recording for like an hour and a half, and none of the audio got recorded, so we're gonna have to do this again from scratch. But now I know how to be maybe a little bit faster. So let's erase all of these, or let's just start from scratch. We'll keep those slides there for future reference, but we'll just go without them. All right, so today we're going to be talking about sines and cosines. As you can probably see from the PowerPoint I have up here, it's not really a PowerPoint, it's just a notebook app. Hopefully, maybe it'll work better than the last one because you can see me draw real time. But anyway, sines and cosines. So you might recognize sines and cosines as, let me draw here. Either you might recognize them as a squiggly line that repeats forever and ever and ever and ever. You might recognize them as the SOHCAHTOA, or you might recognize it as a unit circle measuring tool that tells you either the y value for sine or the x value for cosine. And the question is, how do you consolidate all these definitions together? Because the sine from SOHCAHTOA, the sine here, sine of theta is equal to opposite over hypotenuse, is the same thing as this sine function. And that's the same thing as this mathematical function that helps you find the y value of the circle, of a unit circle. So how do you consolidate everything about that together? There's triangles and circles and squiggly lines all together. So to do that, let's just start with a circle. So I'm going to make a new page here. You might be able to sneak peek into the future by looking at the history of the previous type of video I tried to make. It's on you. But anyway, so let's start with the unit circle. And one thing that I think is not going to change from this and the last recording is that my circles are going to be terrible. But, oh, that's not a bad circle. That's not a bad circle. Okay. So we'll start with the unit circle, which means that it's a circle with the radius of 1 that is centered on the origin of a plane on the xy plane. Right? So that means if it's on the origin and it's 1, that means that this value of x is 1, this value of y is 1, this value of x is -1, and this value of y is -1. Right? So let's imagine we have a point traveling around the circle, this little point here. And it's just zipping around, zip, 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 zip. All the sine function is, so the sine function is just a machine. Well, think of a machine that takes in a point zipping around a circle, unit circle, and spits out the y value of that point. Right? So, and similarly the cosine function, so let me just draw this out. So we have a machine here. I'm just going to do a box here. It's going to be sine of theta. It's going to take in unit circle, point going around. And it's going to spit out y value. Similarly, the cosine function is going to be another machine here. It's going to take the same input, the point going around the unit circle, And that's going to spit out the x value. Right? So let's plot out what these functions are doing. So if we have a circle, one more time, a little smaller, so we have room here, going around, we're going to say that it takes pi amount of time to get halfway around the circle. And that means that it takes 2 pi amount of time to get to the other side of the circle, right? So in half of a pi time unit, it's going to get over here, right? Because if it takes pi to get all the way around, it's going to only take half pi to get up here. And don't worry too much about what it means for a pi time. It's just units of time that aren't conventional. There's different talks about different conventions for how to go around a circle. Some people say tau might be a better unit of time to use for trigonometry. But at the end of the day, pi and 2 pi is convention. It's what everybody uses. So don't worry about why they're there or how they work. Just they're there and accept it, and just understand that if it takes pi to get halfway around the circle, it's going to take pi over 2 to get to the top part of the circle, and it's going to take 3 pi over 2 to get to the bottom part of the circle over here, right? Because it's in quarters. So if we graph out the sine function, so let's start out with sine, what is this going to look like? Well, let's graph it, right? So here we're going to have time, and here we're going to have our y value, because that's what we care about. When time is 0, it's going to start out at 2 pi. It's going to start here at this part of the circle. The y value here is 0, right? Because this is y and this is x. So it's not going to do anything. But then after some time, it's going to move up here, and it's going to get somewhere up here, and then it's going to move all the way up to this point over here. And by this point, the y value is going to be 1. So it's going to gradually get to 1 here. And we'll say this is 1, this is negative 1. And this is going to happen at pi over 2. Then it's going to keep going and keep going and keep going, and gradually it's going to go down to 0 again. So it's going to go up, and then it's going to go down. It's going to happen at the value of pi. And then you can guess what's going to happen here. It's going to go down to negative 1 for the y value at 3 pi over 2, and then go back to 0 at 2 pi, and it's going to keep repeating. So then it's going to just do this. And this is going to be 3 pi over 2, and this is going to be 2 pi. And then you can draw the rest of it out if you want. It's going to go on for infinity on both sides, actually, because you can go in the circle in the opposite direction. So this is our sine function, and already we can see how, maybe if you look back at this first slide, you can try to guess how this value of sine is going to start to relate to this version of sine. But let's do cosine too, just to be safe. And so cosine of theta, that's going to be similar. So here's time, but instead of y, we only care about the x for cosine. So when you're starting out here for cosine, the x value is already positive 1 from the very beginning. So we're just going to put a 1 there, and it's going to have there. After some time, we're going to go up here, and the x value is going to go down to 0. At this point, the x value will be somewhere in between 1 and 0. So it's going to do something like this. And then it's going to go down to negative 1, and then to 0, and then back to positive 1. So you'll see that this is going to do something like this. This is going to happen at pi over 2. This is going to happen at pi. And this is going to happen at 3 pi over 2. And this is going to happen at 2 pi. And then again, this is going to repeat. And you can follow it forever. All right, so here's our sine and cosine functions. And we can already see how the wavy part of the definition of sine relates to the unit circle part of the definition of sine. Because if we're looking at a point here, this length here, this is the value of y, right? The distance from y equals 0 to wherever it is, this is going to be sine And then this distance here from this point, this is going to be cosine. So the big point to remember throughout all of this tonight is just that sine and cosine are just simple functions that spit out the x and y value of a point going around a unit circle. That's it. That's the big thing. The other big thing is how this relates to right angle triangles and what this has to do with SOHCAHTOA, which is what we're going to go out right now. But the first thing I want you to remember is just sine and cosine are not complicated abstract figures. It's just a machine. You put in a circle and it spits out an x or a y value. And it just so happens that it looks like a curvy line because nature likes to do things in curvy lines. You won't see nature just go whoop and then change back. No, I'll change the camera. Okay, there we go. So let's quickly talk about SOHCAHTOA here. I want this to be a lot shorter than the last recording because the last recording was pretty long. Okay, so how does this relate to SOHCAHTOA? So let's just think of a right angle triangle, any right angle triangle. Let's get this guy over here. And any right angle triangle with one angle that you know, theta, is going to have three sides, right? It's going to have the hypotenuse. The hypotenuse is always going to be opposite of the right angle. It's going to have a side that's opposite of the theta, which is we're just going to call O for opposite. We're going to do hype. O. And we're going to do adjacent. Right? Now, if you know what theta is, how do you know how can you figure out what any of the other stuff are? Surprisingly, sine and cosine, and even tangent, but we'll talk about that next time. But sine and cosine are helpful for right angle triangles, even though they're just only purely defined by circles. And this is how. So let's just, for the sake of argument, and let's just divide everything. Divide all side lengths by the length of the hypotenuse, so by h. What does that leave you with? Well, it's going to be a smaller triangle, right? Because you're dividing all the side lengths. The angles are going to stay the same. So this will still be theta, this will still be a right angle. But instead of h up here, it's going to be h divided by h. Here, instead of opposite, we're going to have opposite divided by h. Instead of adjacent, we're going to have adjacent divided by h. Well, h divided by h is just 1, so we can just write that. And what you'll notice here, I'll write this down, notice we have a triangle with a side length of 1. What does this mean? It means we can squeeze this into a unit circle. And this is good because we can use the tools we developed for the unit circle to help us learn more about this triangle. So let's squeeze it into a unit circle. So let's squeeze it into a unit circle. If we do that, we're going to end up with, I wonder if this is going to work. Yeah, this will work. I'll put the unit circle here, and more importantly, we're going to put our right angle triangle that we drew over here. And this is our angle theta. This is our right angle, and we know that the length of the hypotenuse is 1, so we know that it fits in the circle because the circle has a radius of 1. And here we have O over H. Here we have A over H. And now, if we go back to, where is it? Here, we can see that the function that determines the height of the point is also the function that determines the y value of the point is this line over here. If the point was over here, sine would be over here, and cosine would be over here. It would still be a right angle triangle. If the point was somewhere over here, this would be y, and this would be x, and this would be a. So no matter where your point is in the circle, you can draw a right angle triangle here, and you can make it so that the vertical line is going to be the sine and the horizontal line is going to be the cosine, because that's just what the functions are defined to be. So we know that this O over H is also equal to sine of theta. And we know that this A over H is also equal to the cosine of theta. And this is where the famous SOHCAHTOA comes from. We'll talk about the tangent part of it later, as in next time, not today. But here we see that sine of theta is equal to O over H. Cosine of theta is equal to A over H. And then we'll learn later that tangent of theta is O over A. And we remember that as SOH, CAH, TAO. SOHCAHTOA. Sorry, you got SOHCAHTOA. Let's fix that. Let's get rid of that. Ah, jeez. SOHCAHTOA. Sure. SOHCAHTOA. And the reason why this works is because by dividing all the side lengths of the triangle here by H, we're rescaling the triangle. And by rescaling the triangle, we're able to squeeze it into a unit circle, and then we're able to use our tools for sine and cosine to solve anything that we might need using SOHCAHTOA. Really, what SOHCAHTOA is just a way to rescale our triangle without having to actually sit down and do it. Like if you didn't know what SOHCAHTOA was, you could derive the answer by manually rescaling and drawing it in the unit circle and figuring out what everything was. But we don't need to do that because SOHCAHTOA is easy to remember. It's the one thing everybody comes out of Trig remembering fully. But I think the main point I want to express tonight before we end, because this is really all I want to say. So two big points for tonight. One, sine and cosine are just functions that describe the x and y values of a unit circle. Sine that describes the y value, cosine describes the x value, and as the point goes around the circle, it changes gradually and it goes on forever. So that's super simple, nothing complicated. Don't overthink it. Don't think it's anything other than it is because of its appearance in more complicated equations. At the end of the day, a sine and a cosine is exactly what they are. They're going to be expanded upon, and we're going to use them in complicated ways later, but that's not the point. This is what they are, and don't lose track of that. Number two, the reason why they show up in triangles is not because trigonometry is about triangles, but it's because triangles, they just fit in a unit circle pretty well. Trigonometry is about circles. What we're going to learn about trigonometry and its identities is just circles, and they just happen to. It just happens to be nice for triangles. But one quick thing I guess we should do before we call it a day, since we have a minute or two, is so let's look at this triangle again. So let me just make a new slide here. This is going to be fun. This is just for funsies now. If you have a right angle triangle, and you know that this side is sine of theta, you know that this side is cosine of theta, and since it's in the unit circle, you know that this side is equal to 1. What happens if we apply our friend Pythagoras to this triangle here? The Pythagorean theorem says that a squared plus b squared is equal to c squared, right? Well, c squared in the Pythagorean theorem is the hypotenuse, so we'll just plug that in. So 1 squared instead of c squared. A squared and b squared are the two side lengths, so sine squared plus cosine squared is equal to 1 squared. And then 1 squared is just 1 times 1, and that's just equal to 1. So we can just write it as down as just a 1. So we're left with sine squared of theta plus cosine squared of theta is equal to 1. And this is kind of wonderful. This is going to be an identity that we're going to be using a lot, because this means that if we know what cosine is, we can figure out what sine is. And if we know what sine is, we can figure out what cosine is, because they're both equal to a constant, 1. And this will make a lot of future identities easier to derive, and it'll make a lot of future problems easier to solve, because you can figure out the other if you know one. But that's just extra. Important things, yeah, I already talked about them. Yeah. So sine and cosine, not complicated. I think they're kind of interesting, and just the way that they show up all over nature without um, being prompted to, I guess. I'm ranting at this point, so I'm going to let you guys go. You guys have a wonderful future, and I'll see you around in the future. Bye.